ETC. Recognize this ETC depiction as an energetic one, just a cartoon, showing that electrons are passed through that electron transport chain, bing, 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 through the chain, where they're used to tap into to make a proton motive force. So there's our ETC to generate a PMF. That PMF, of course, just as we've seen in all other cases, can then be tapped into to make ATP. This is the third and final type of phosphorylation. So let's take a moment for a quick review. We've had two types already. This is going to be our third. So first type of phosphorylation was substrate level. In substrate level phosphorylation, we saw that a high energy donor, such as phosphoenolpyruvate, transfers a phosphoryl group in an exergonic way onto ADP to make ATP. Number two was oxidative, or oxphos. In oxphos, the energy comes from electron transfers, from ripping and stripping electrons off of a high energy molecule, and then transferring them onto reducing power, NADH, FADH2, and getting them to the ETC to make a proton motive force to then allow for the synthesis of ATP. Now, in photosynthesis, this is very similar to oxphos. Many of the same things have happened. The difference is that the electrons were excited by light. So rather than calling it oxidative phosphorylation, we call it photophosphorylation, right? So this is our third and final type of phosphorylation. Photophosphorylation, let's write that down in our notes here. This is photophosphorylation. Now, the way in which the photosystems are designed depends upon the type of bacterium. The green bacteria, the purple bacteria, they actually only have one photosystem. However, the cyanobacteria actually have two photosystems. And so I want to talk about the complexities of oxygenic photosynthesis and those that have two photosystems that are very creatively named photosystem 1 and photosystem 2. Not creative at all. But let's talk about that. So oxygenic phototrophs have two types of photosystems named photosystem 1 and photosystem 2. And they use these differently. So in my picture, photosystem 1 is the photosystem on the right, photosystem 2 is the one on the left. They're both going to play a role depending upon the needs of the cell. Sometimes only photosystem 1 is used. The time when only photosystem 1 is used is when a cell needs to generate only ATP, but it doesn't need any NADPH. Then it taps into only photosystem 1. So if a cell only needs ATP but not reducing power, then it will use photosystem 1. And the process that it uses is quite fascinating. It's called cyclic photophosphorylation. And I'm going to go through that blow by blow so that you can see all that's going on there. So in cyclic photophosphorylation, what will happen is that, as we talked about before, light hits the antenna complex, energy is transferred, bing, 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 down the sink or the funnel to the reaction center chlorophyll. Electrons are excited to the top of an electron transport chain, right, the energetic top. They transfer their electrons through that electron transport chain. And as a result of that electron transfer, protons are pumped, a PMF is formed, and ATP can be synthesized, right? And that's what this passage is saying here. But now the thing that makes this cyclic photophosphorylation is the fact that the electrons, after passing through the ETC and being used to make ATP, are recycled. They're literally recycled. So they're passed back to the reaction center chlorophyll, where then they can be excited again and be used to make ATP again and recycled again, and all of this happens in a cyclic way, right? So that's where that name comes from, cyclic photophosphorylation. So in this case, photosystem 2 is not tapped into, it's not needed for cyclic photophosphorylation. But sometimes a cell needs to make reducing power. That is, it does need to make NADPH. So when a cell does need to make NADPH, that's when it's going to bring in photosystem 2. So let's see how all of that works. And I bet you've already guessed by now that this process is called non-cyclic photophosphorylation. So when both ATP and reducing power are needed, then this process called non-cyclic photophosphorylation is utilized. So in the same way that we started cyclic photophosphorylation, picture light hitting the reaction center chlorophyll, the antenna complex first, being transferred to the reaction center chlorophyll, energy being used to excite electrons, electrons passing through the ETC, but this time, rather than those electrons getting recycled, getting used to make ATP, instead they're usurped somewhere along the way, and they're used to reduce NADP plus to NADPH, making reducing power, right? So wait a minute, that means that the electrons aren't available to be recycled again because they're on NADPH. We know that's carrying the hydride anion. It's carrying 2 electrons. They're not there to be recycled back to the reaction center chlorophyll. So this reaction center chlorophyll right here has to come up with another way to get its electrons. Well, it gets them, turns out, from photosystem 2. So photosystem 2 says, okay, here, take some electrons. It transfers those electrons over. And in doing such, it leaves photosystem 2 without its electrons. But not before photosystem 2 did something with those, because in fact light also hit its antenna complex, was also transferred to the reaction center chlorophyll, also excited electrons, and those electrons passed through an ETC where it was used to make a PMF and to make ATP. So ATP was made from photosystem 2's electrons before they were passed to photosystem 1's reaction center chlorophyll. So look at this, we've made both products of light reactions of photosynthesis. We've made NADPH and we've made ATP. ATP from photosystem 2, NADPH from photosystem 1, and we've replenished the photosystem 1 electrons. So we're at least mostly there. But we're not quite there because remember now what happens to photosystem 2? It doesn't have any electrons to make ATP. So it's going to have to get them from an outside source. And if these are oxygenic phototrophs, you guessed it, it strips them off of water, making oxygen as the product. So here's where that water electron donor finally comes in. It is oxidized by photosystem 2. It is utilized to deliver electrons to that photosystem, and we recognize this as being the full glory of non-cyclic photophosphorylation, right? Both photosystem 2 and photosystem 1 used. Quick recap, photosystem 1 uses its excited electrons to reduce NADP+, making reducing power. Photosystem 2 uses its excited electrons to make ATP, but also to replenish photosystem 1's electrons, leaving photosystem 2 with no electrons, meaning it has to rip them off of water and in order to continue. So this is why oxygenic phototrophs require water. They can't live without it. So let's go ahead and look at a model now. And this was a model that one of my students made last semester. Oh my gosh, I was so excited that she made this model because photosynthesis can be pretty hard to understand. So let me pull over her model and you guys can take a look. This is photosystem this is photosystem 1. Here we're seeing cyclic photophosphorylation. So she's showing the recycling of electrons in a circular way. I love how she did the antenna complex and she used a button, a big green button to represent the reaction center chlorophyll. Just awesome, awesome model there. And so you can see the cyclic photophosphorylation there. I'll leave this also in the lab. This is available in the lab. But then on the other side, look at this. She did non-cyclic photophosphorylation. So you can see that she's got the whole process of getting electrons from water to replenish photosystem 2's reaction center chlorophyll there. And she's showing the generation over here of NADPH. So she's got the whole 9 yards going with this model. And once again, I'll bring that to lab so everybody can really fully appreciate it in all its glory. Nice. So you might think we're done, photosynthesis done. But notice what we've done in the light reactions is to make NADPH and to make ATP, right? But we haven't talked about how those can be harnessed to then make organic sugar. That is, we haven't looked at the dark reactions of photosynthesis. You're going to recognize this, and I know I remember talking to April as she was taking the exam. You'll recognize the dark reactions of photosynthesis because you've actually seen what we call the Kelvin cycle before. Let's write down, though, first the net reaction. You guys, again, you recognize this too, because remember when we were talking about the combustion of jelly donuts? This was the reaction that we showed. So remember that reaction there. But remember, I think, and I'm trying to remember who this was, Spencer or somebody, maybe Schwa, I can't remember. But remember that the reverse of this reaction is the one that typifies photosynthesis. So photosynthesis is the reverse of our combustion reaction, meaning that for photosynthesis it is an energy consuming reaction. And remember, I'm pretty sure it was Spencer who said you reverse the sign on that. 686 kilocal per mole will be what represents photosynthesis. So photosynthesis, rather than being exergonic, is endergonic. So let's look at how we might contrast the dark reactions of photosynthesis with the oxidation of sugar by a chemoheterotroph. So let's just write down what's true of photosynthesis. So photosynthesis is anabolic. So the dark reactions of photosynthesis, the Kelvin cycle, will be anabolic, not catabolic. That is, it's a building set of reactions. It's going to be reductive, not oxidative. That is, it's going to consume reducing power, not make it. It is going to be endergonic, not exergonic. That is, it's going to consume ATP, not produce it. Okay? So recognize this massive contrast between the Kelvin cycle. Say, if we contrasted the Kelvin cycle with the TCA cycle, these are important ways in which we would want to contrast those two cycles. Okay, so a biosynthetic cycle is the Kelvin cycle versus a primarily catabolic or breakdown pathway, which is the TCA, even though we know it makes precursor metabolites, right, that makes it amphibolic. So what other group of organisms must be able to fix carbon? We know this right off because we started there. Anything that is called an autotroph, so not just photoautotrophs, but also chemoautotrophs, are rock eaters. Excellent. Let's now take a look at the Kelvin cycle. In the Kelvin cycle, which here's the net reaction, the thing that I want to draw your attention to is the massive consumption of ATP, 18 of them, and reducing power, 12 NADPH, just to make 1 6-carbon sugar. Holy cow! 18 ATPs, 12 NADPHs just to make 1 6-carbon sugar. Check that. So let's look at one turn, or actually let's look at 6 turns of the Kelvin cycle that allows that to happen, because it's got to turn 6 times in order to allow the synthesis of 1 6-carbon sugar. So the input of 18 and 12, the first portion of the Kelvin cycle is called incorporation. In incorporation, the inorganic CO2 molecule is brought in. This is not unlike the TCA cycle, where a smaller molecule is brought in and bonds are formed. It's a condensation reaction, it's a synthesis reaction. One thing that is different in this first reaction of the Kelvin cycle is that after this, these carbon dioxides are brought in and added to this ribulose 1,5-bisphosphate, that is going to synthesize a 6-carbon molecule that is actually going to go ahead and then split down into 2 3-carbon molecules. It's sort of this just spontaneous process that happens. Some of you will recognize the name of the enzyme that catalyzes the incorporation step. It's called rubisco. And I know, gosh, poor Josh Ladwig, this is, you know, you're the photosynthesis expert, and I know this is very trivial for you. So I apologize if it's been a boring day. Josh is your expert. If you guys have any questions for him, he's studied photosynthesis for 6 years, right, Josh? So he'll recognize the name of rubisco, the enzyme that catalyzes the incorporation step. And notice that this then makes something that looks familiar to us. It makes a molecule called 3-phosphoglycerate. And hopefully everybody's working on their posters, their metabolism posters, and you recognize that as an intermediate of glycolysis. In fact, it's the intermediate of glycolysis that's formed in step 7 when 1,3-bisphosphoglycerate is hydrolyzed to make ATP. So look at this. These steps in the next portion of photosynthesis of the dark reactions of the Calvin cycle, they're the opposite. They're the reverse of what we saw in the glycolytic pathway. So rather than producing ATP, it's consuming it. So it's consuming the ATP, and we see it going in the reverse, making 1,3-BPG, which then can be converted using a lot of reducing power into glyceraldehyde 3-phosphate, which we also recognize, which is the precursor metabolite to make the 1,6-carbon sugar. So this step, this set of steps in photosynthesis or in the Calvin cycle is called reduction and synthesis, making sense because it is the portion in which we see the synthesis of that 6-carbon sugar. After that, look at this. Notice that I'm being simplistic here because there are many steps that happen next. So we're leaving out a lot of those. But in the next portion of the reaction, we see the consumption of more ATP just to regenerate the initial molecule with which the CO2 reacted. And in fact, this is called regeneration. So the Calvin cycle, as it turns, can be split into 3 portions: incorporation, reduction and synthesis, and then finally regeneration. So this is the process whereby the energy and the reducing power, the ATP and the reducing power made in light reactions is harnessed to finally make this 1,6-carbon sugar. A very, very endergonic process consuming 18 ATP and 12 NADPH. Wow, man, that is a great example of an anabolic pathway. So that coverage ends our consideration of photosynthesis, and it's a great segue into the next section where I want to talk more about anabolic pathways. We could spend a full semester doing that, and so my highlights here are just that. They're just highlights. But I want to, with the principles in mind that we saw in the anabolic pathway of the Calvin cycle, I want to take that knowledge and apply it broadly to our large poster view and think about ways in which anabolism can run in all of these varying pathways, and maybe look at sort of a skeleton outline as we're seeing in this picture, and recognize that many of the catabolic pathways that we talked about were amphibolic, right? And that they too could generate precursor metabolites that could be used in anabolism. Let's just look at a few examples of molecules that can be used as precursor metabolites that can be used to synthesize molecules in anabolism. So if we look at the TCA cycle, steps 1, 2, 3, and we recognize that alpha-ketoglutarate is generated in the third step there, alpha-ketoglutarate can be used to synthesize both glutamate and aspartate. So it can be used as a precursor metabolite in the anabolic pathway that synthesizes these 2 amino acids. Succinyl-CoA can be used as a precursor metabolite to synthesize porphyrins, important in the ETC. Also, many others of the intermediates, such as oxaloacetate, can be used to synthesize also amino acids, for example, methionine and threonine. It can also be converted backwards into pyruvate, and pyruvate can be used to synthesize glucose in the backwards pathway. So eventually, if this pathway is followed all the way backwards, we can get the synthesis of glucose in the anabolic pathway called gluconeogenesis. Many of the intermediates of the pentose phosphate pathway can be used to synthesize aromatic amino acids. Also recognize that glyceraldehyde 3-phosphate dihydroxyacetone phosphate can be used to make the backbones of fatty acids. I'm going to abbreviate that, fatty acids. Also, too, acetyl-CoA can be used to build up the fatty side chains of a fat, so fatty acid synthesis. Man, there's no end, is there? Pyruvate. Pyruvate can be used to synthesize alanine. There are so many biosynthetic pathways within a cell, and if you want to read a little bit more of that, your text goes into even greater depth on many of those things. So feel free to take more time with this. We're simply scratching the surface, and let's take just a moment to write down what we've shown in picture view and maybe that you've added to your poster. So we'll just jot a few notes. Fatty acids are synthesized from acetyl-CoA when two carbon groups are added to a constantly elongating chain. It's held by a protein called acyl carrier protein, which I mentioned because it's cool. It has what's like almost like a long elephant trunk that it can use to get more and more two carbon groups on it. Glycerol synthesized from dihydroxyacetone phosphate, the glycerol backbone, so we talked about that. Amino acids from a variety of sources ranging from the pentose phosphate pathway to glycolysis to the TCA cycle. So things like glutamate and aspartate, we talked about alpha-ketoglutarate being the precursor metabolite to their synthesis, and we talked about aromatic amino acids such as phenylalanine coming from the pentose phosphate pathway intermediates as precursors. And oftentimes in these biosynthetic pathways, you guys already know this, feedback inhibition is also often an important thing. The products, if they accumulate too much, that is, if there's too much glutamate, it'll feedback, inhibit the enzymes that are used in the biosynthesis of that amino acid. And nucleotide synthesis, man, it's so complex that we're just going to say it's really complex. And that's how we're going to leave it today in our discussion of anabolism. So today is both a happy and a sad day, I guess, because it is Friday, but also it's a little bit sad because we're leaving metabolism behind. So this for you is your cue to spend some good time making that metabolism poster. And I know, Erin, you've already gotten started on yours. Feel free to use some of the posters in the lab to help you out with that process. And use me as a resource as well, and your TAs and your SI leaders, they can help you build the best poster possible to make it so that your third exam is the best ever, because on your third exam, you will be allowed to use your metabolism poster. Pretty sweet deal. Have a great weekend.